Okay, so welcome back to another video. So here today we have a partial product series of gamma of k over 3, where our index k is equal to 1 and our upper index is 8, and we actually want to evaluate this series. So interestingly, if you were to plug this to Wolfram alpha, it only gives you two things. It only gives you the decimal approximation and the series expansion, which doesn't give you too much because we want to find the exact value, but it doesn't even help since the decimal approximation doesn't give you exactly if there was some sort of, closed algebraic expression that is, defined to be the exact value. So that's what we're trying to do here. With this gamma function, of course, there's going to be a couple formulas we will be using to help, compute our series as well. One of the most important ones being the Euler's reflection formula, which I covered it. I actually covered the proof of that in a video, so if you want to check that out, the link will be in the description below. So there's nothing more to be said. If we were to, after getting the exact value we want of that closed form of our partial product series, it also should match that. If you were to plug the evaluation into that calculator, it will get the exact decimal approximation that this is provided. So let's just jump right in. So if we were to expand this out, so let's see, one term at a time. So we have gamma of 1 over 3 multiplied by gamma of 2 over 3 multiplied by gamma of 3 over 3 multiplied by gamma of 4 over 3. And let me move on to the next line. The product expansion continues. So we have gamma of 5 over 3 multiplied by gamma of 6 over 3 multiplied by gamma of 7 over 3 and then multiplied by gamma of 8 over 3. So this is what the expansion looks like. So now we need some formulas to actually help establish in order to help evaluate this series over here. So let's actually do that. So the first formula we'll be using is Euler's reflection formula. Of course, that says for n is not an integer, then we have that gamma of n multiplied by gamma of 1 subtract n is equal to pi, then divided by sine of n times pi. You will be using this a lot more. So the next formula we'll also be using is its recurrence relation that says for n is strictly greater than 0, that gamma of n plus 1 is equal to n then times gamma of n. So from here we'll actually just, we got these two formulas we want that's going to be very important to use in order to help utilize the changes we need to make. So now let's actually focus on some of the expansion, how we can actually fix this up a little bit. So let's focus on gamma of 1 over 3 times gamma of 2 over 3. You'll notice that if you were to look closely by using Euler's reflection formula, we can say that we could just plug n is equal to 1 over 3 and it still satisfy this formula. So therefore I'll just say that this is actually just pi, then divided by sine of, we said n is equal to 1 over 3, so this will be pi divided by 3. With this, that's great. Next thing we have is gamma of 3 over 3, which is the same thing as gamma of 1, which that's a well-known value that it's actually just equal to 1. Next we'll pay attention to is gamma of 4 over 3, which interestingly we will be using that recurrence relation, because notice that 1 or n plus 1, we could just substitute n is equal to 1 over 3. So this will be 1 over 3 times gamma of 1 over 3. Okay, so that's great. Now next thing, gamma of 5 over 3. Yeah, actually just do the same thing again, except the n will be 2 over 3 and then multiplied by gamma of 2 over 3. Next is gamma of 6 over 3, which in other words, that's just equal to gamma of 2. I'm going to leave this as an exercise for you. Basically, all you need to do is just, use the integral representation of gamma and then just compute from there. But this is actually going to equal 1. Then next we have gamma of 7 over 3, which again, we'll just use that same recurrence relation. We'll plug this for 4 over 3, and so we'll have multiplied by gamma of 4 over 3. And then lastly, we have gamma of 8 over 3. And so this time our n will be 5 over 3, and then multiplied by gamma of 5 over 3. We already figure out our gamma of 1 over 3, 2 over 3, 3 over 3. So now there comes, the rest. Well, also, we already know what gamma of 6 over 3 is as well. So we have these four we need to, figure out. So here's some notes that we're actually going to make over here. And this is simply just, observation. So if we look at the product of gamma of 4 over 3 and then times gamma of 5 over 3. So let me first put that down. 4 over 3 times gamma of 5 over 3. We notice that if, just plug in the substitution. So this is 1 over 3, gamma of 1 over 3, multiplied by gamma of 2 over 3 times gamma of 2 over 3. So then we notice that we have a gamma of 1 over 3 and gamma of 2 over 3, but simply we actually just showed that this is just equal to pi divided by sine of pi over 3. So we can actually just substitute that back in. And so what we're left with is just we have 1 over 3 times 2 over 3 and then times pi divided by sine of pi over 3. Next thing we need to analyze is the 7 over 3 and then 8 over 3, which again, it actually just follows the same rule as the previous, but there's actually more to it than you think. We notice that just substituting this back in, so 4 over 3, gamma of 4 over 3 multiplied by, so 5 over 3, then times gamma of 5 over 3. So we notice that we just look at these two products together. This is basically the same thing as this, which we just established that this is just equal to 1 over 3, or this expansion over here. So again, just do that substitution. So now all we have to do is, well, I already said it, do the substitution. So we have 4 over 3 times 5 over 3 times 1 over 3 times 2 over 3, and then times pi divided by sine of pi divided by 3. So we have everything we need. So now let's actually just go back and do the substitution of our expansion over here, which is of course the given. So now just to reiterate everything, so now we have the partial product k is equal to 1 of gamma of k over 3. So let me actually just put this back in, put this in black so we know what we're dealing with. So now first comes gamma of 1 over 3 and 2 over 3. So that will be, pi divided by sine of pi divided by 3. Next, we have gamma of 3 over 3, which we just set that that's equal to 1. So we don't really need to put that over there. Same thing for 6 over 3. That's also equal to 1. So we can exclude that. Next, we have 4 over 3 times, or gamma of 4 over 3 times gamma of 5 over 3. So we said that this was equal to this. So let's actually just plug this back in. So we have, I'll actually simplify this. So we have, or combine these together. So we have 2 times 3 squared and then times pi divided by sine of pi over 3. And then lastly is our, because I said that gamma of 6 over 3 is just 1. Lastly, we have our 7 over 3 and then 8 over 3 for gamma. So just substitute everything back in. 4 times 5 times 1 times 2, then divided by, so this will be 3 to the power 4, and then multiply it by pi divided by sine of pi divided by 3. So now further simplification, there's you have 3 times of sine of pi over 3. So this will be, and then same thing for pi as well. So pi cube, then divided by sine cube of pi divided by 3. Then we just multiplied this with, so this is 2 times 4 times 5, 40, then times 2, which is 80, and then divided by, so 3 squared and then 3 to 4, so 3 to the 6. Simply simplify this even further, we know that sine of pi over 3 is just equal to square root of 3 divided by 2. So we, take the third root of, or if we cube that, so and then flip the reciprocal. So now we would have that this is 8 times pi cubed times 80, and then divided by, so put this as the square root of 3, then cube, then multiply by 3 to the power 6. Further simplifying this out, so this will be 640, then divided by 3 to the power 6. Then we just enclose this with the parentheses and say that this is just pi, and then divided by the square root of 3, and then cube. Or if we want to further simplify this even further, we can, because we can actually just move the 3 to the power 3 inside the quantity over here. So we have 640 divided by 3 to the power cube, then multiplied by pi divided by 3 times the square root of 3, and then cube. And so there we have it. We actually just finished the computation. And if you were to plug this in Wolfram Alpha, it actually is exactly the decimal approximation. So let me actually circle these two, or box these two, because they're technically the same thing. One's just simplified even further. So whichever these two answers, your choice, they still equal the same. So there we have it. So yeah, that's pretty cool if you ask me.